Today, in this series of lectures, I shall discuss the relations between temperature, pressure, volume of ideal gases in a reversible adiabatic process. From the first law of a TD, we have the relation for ideal gas, this Q equal to CV dt plus a PdV, when the work is mechanical only. And this is the work done by the gas, and it is the temperature. Q amount of heat is supplied to this system containing 1 mole gas, and this absorbed heat, the supplied heat, will do some mechanical work and increases the temperature by dT amount. Cv is the molar heat capacity at constant volume for that gas. For adiabatic process, Q equal to 0. So 0 equal to Cv dt plus PdV. This will be the starting equation for our formulations of this relationship between temperature, pressure and volume in adiabatic reversible process. Now I like to first find out the relation between temperature and volume. In this case, this is the ideal gas, and for 1 mole ideal gas, PV equal to RT, or P is equal to RT by V. As we are trying to find out a relation between temperature and volume, and P is to be eliminated by the use of this equation of 1 mole ideal gas, and P equal to RT by V. So this will be 0 equal to Cv dt plus RT by RT into dV by V. I am putting the side chain minus Cv dt equal to RT dV by V, or minus Cv dt by T equal to R dV by V. Now, since this process is reversible, all the parameters are changing by infinitesimal amount, or this changes continuously. So we can put this integration of these two terms, and assuming this Cv is constant independent of temperature, we can write dt by T equal to here R dV by V. R is the universal gas constant. So doing this definite integral T1 to T2, and here V1 to V2, we are having the integration minus Cv ln T2 by T1 equal to R ln V2 by V1. dividing by Cv, then it will be ln T1 by T2, and this is equal to R by Cv and ln V2 by V1, or ln T1 by T2 equal to ln V2 by V1 and whole to the power R by Cv. So eliminating this ln terms from the both sides, we have this relation T1 by T2 is equal to V2 by V1 and to the power R by Cv. However, this R by Cv we can write Cp minus Cv. The value of Cp minus Cv for this ideal gas is equal to R, and this is by Cv. So it is a Cp by Cv minus 1 or gamma minus 1. Gamma is the molar heat capacity ratio. So instead of writing R by Cv and multiplying this cross section in a cross section way, then it is T1 and V1 to the power gamma minus 1 equal to T2 and V2 to the power gamma minus 1. So this is the relation between this temperature volume for this ideal gas in reversible adiabatic process. And these sort of equations have many benefits. In many benefits, suppose I can show one problem. Say, in a cylinder, the gas is either nitrogen or this neon. Either the gas is nitrogen or a neon. N is seen on the label of this cylinder, but due to long time, but this 2 or E, these two are blurred, would not be seen, and I shall have to identify, suppose, whether it is nitrogen or it is a neon. So I can do one experiment. This some amount of this gas is put in a reversible adiabatic process, and suppose 5 liter of the gas of this gas at 25 degree centigrade. When it is done, undergoes a reversible adiabatic process to 6 liter volume, and temperature falls to 4 degree centigrade. And then the question is find the gas, whether it is nitrogen or this neon. So I can do this problem by the use of these relations. Say here T1 is equal to 298 Kelvin and V1 equal to 5 liter and T2 equal to 277 Kelvin and V2 equal to 6 liter. If we put here all these terms, then gamma would be calculated, and suppose gamma is found to be 1.40. This shows that the gas actually is nitrogen and not neon. For if it would be neon, then gamma will be equal to 1.66. So this is a simple experiment. By the use of this relation, we could be able to identify this gas as nitrogen is a diatomic gas, and for the diatomic gas it is 1.40, the value of gamma. Similarly now, so I can write here this T1 V1 to the power gamma minus 1 equal to T2 V2 to the power gamma minus 1, and this is the equation number. This is the first part. Now I like to, in a similar way, find the relations between P and V. This is the starting equation. I can take it, and here dt is to be eliminated. This equation must contain pressure and volume terms. So for this, let us take this ideal gas PV equal to RT for 1 mole, or full differentiation. It is PdV plus VdP equal to RdT. So instead of writing this PdV, instead of writing this dt to be eliminated, here. So instead of dt, we can write PdV plus VdP and divided by R. So putting here this 0 equal to CV by R into PdV plus VdP and plus PdV or equal to CV by R PdV plus CV by R VdP and plus PdV, or again PdV taking common, CV plus 1 divided by R, CV plus R and PdV equal to CV by R VdP. So this is 0 equal to list. R can be cancelled. So this one and CV plus R equal to CV plus CV minus CV for this ideal gas. So this will be CV. So this term R cancels, and so this one is CP PdV equal plus CV and VdP. Now putting the side change, doing the side change and separating the variables, we have this minus CP by CV, and here this dV by V coming here, and this is equal to this dP and divided by V. or this Cp by Cv equal to gamma or minus the gamma, and doing this integration as the process is reversible, dV by V, here V1 to V2 equal to integration dP by P, here P1 and P2. So this will again be ln P2 by P1, this part written first, and equal to minus is removed, or let me write minus ln V2 by V1. If we remove this minus, then it will be gamma ln V1 by V2, or this again could be written as ln V1 by V2 to the power gamma. To the power gamma. So, eliminating these two ln terms from the both sides, we have P2 by P1 equal to V2 by V1 by V2 to the power gamma, and the relation becomes P1 and V1 to the power gamma equal to P2 V2 to the power gamma, or we can write this PV to the power gamma is equal to constant. Here also similarly, T V to the power gamma minus 1 is also equal to constant. So this second part, PV to the power gamma is equal to constant. Then this is a third relation. Then this third relation, could be done in a similar process. And now the relations between temperature and pressure. This is the starting equations. And for the ideal gas, PdV plus VdP equal to RdT. Here I shall have to replace this dV terms to be replaced, and again in a similar way the integration, there will be a separation of variables and the integration to be done, and after side change, and these relations will give this T to the power gamma and P to the power T1 to the power gamma and P1 to the power minus 1 minus gamma is equal to T2 gamma and P2 to the power 1 minus gamma, or I can write T gamma and P 1 minus gamma is equal to constant. So these are the three relations. These are the three relations to be found between temperature pressure, temperature volume and the pressure volume for this ideal gas in a reversible adiabatic process. These relations are very much helpful, and I can show in this next lectures how these relations could be used in different calculations or derivations. Now I can show in a PV diagram. Suppose this is the PV diagram, here P and here V. And suppose there is one gas, one ideal gas, process is reversible as we have done earlier, and these two gases have taken in the same initial state, and they are conducted. One is a reversible adiabatic process and another is a reversible isothermal process. This adiabatic process and reversible process, these two are the main processes in thermodynamics. Whenever it is the isothermal, suppose isothermal expansion, or I can say a reversible isothermal expansion of an ideal gas. So in this relation, PV equal to constant, very famous Boyle's law for the fixed amount of this gas. And PV in a reversible process, PV, pressure versus volume, will be the rectangular hyperbola curve. And this curve is, suppose this is the starting point, and starting point P1, V1, and this it is the rectangular parabola, and this curve final pressure is P2 and V2, means this is V2 and this one this is V1, and the gas at the initial state P1 Q1, and after this reversible isothermal expansion, this final pressure P2 and final volume P2. Now I like to see the graph for this, for a reversible adiabatic expansion of the ideal gas, same ideal gas, from the same initial state, In this relation, for this adiabatic relations, PV to the power gamma equal to constant. Gamma is the molar heat capacity ratio. So if we again do this curve for this adiabatic process, since the reversible, so this continuous curve will be there also. If it would be irreversible, then intermediate states are not known, and so we shall get only the initial state and final state, and not this intermediate states, and we could not draw this curve. So for this adiabatic process, and suppose this curve is like this. This is for this isothermal curve, and this is for the adiabatic curve. And here the pressure is suppose P2 dash and P2 for the same volume change of this ideal gas in two different processes, final pressures are different, though they are started with this same initial pressure, same initial volume. P2 dash will be less than P2. Why? The reason is very simple. For this isothermal process, the walls of this system are dithermal. Heat is coming from this surroundings to the system for its expansion. But in this case, walls are wrapped with a good insulator, so heat cannot enter from the surroundings to the system. As a result, there will be fall in temperature for this adiabatic expansion. Final temperature in adiabatic expansion is less than it would be for this isothermal process. So whenever the temperature falls, volume change same. Temperature falls, the pressure of this final pressure of this ideal gas for this reversible adiabatic process becomes also less. P2 dash is less than P2. P2 dash is less than P2. How could we prove it? This is the explanations of P2 dash will be always less than P2, but it could be also explained in terms of the mathematical way, and mathematical deductions will be better. And if this one, the adiabatic curve is steeper, means the slope of this adiabatic curve is greater than slope of this isothermal curve. So this slope del P by here, slope is dP by dV in this adiabatic process is greater than dP by dV for isothermal process. Since this curve, this adiabatic curve is steeper, so its slope will be greater than the isothermal. Then we shall have to calculate by the use of these two relations. For this isothermal process, it is PdV plus VdP and constant differentiation equal to 0. Or dP by dV for this isothermal process equal to minus P by V, equation say A. And for this adiabatic process, this is the relations. So I can do logarithm ln P plus the gamma ln V equal to ln, and suppose this constant C, and so ln C. Then taking this difference, doing this differential, or here 1 by P and dP plus gamma by V into dV equal to 0, constant differentiation equal to 0, or dP by dV at in this adiabatic process is equal to minus P by V minus P by V, and gamma is always greater than. So if we take this ratio, dP by dV for this adiabatic process, and here dP by dV for this isothermal process, this will be gamma, and gamma is always greater than 1. So this one is greater value, having greater value than this one. This can flow mathematically. I can show another problem here. Suppose adiabatic expansions is there, and what will be the curve? Similarly, what will be the curve? And if this curve, if this plot is here, the plot is P versus V. If we do the plot V versus P, then what would be the nature of this curve? Suppose side by side I can write here P and here V, and the starting point is same, say P1 and V1 is the starting point, and volume is increasing and pressure is decreasing. So this will be rectangular hyperbola. This will be the rectangular hyperbola for this isothermal process, and here the pressure P2 and volume V2. This is the volume V2 and this is the volume V1. This curve is coming from this to this, And for this adiabatic process, this curve will be like this. Now this is the adiabatic process. And this is what this is for adiabatic process, and this is for this isothermal process. And in this case, the initial volume, final volume same, but this is P2 dash and P2. So final pressure for this adiabatic process is less than the final pressure for this isothermal process. And here also the adiabatic curve is steeper than isothermal. It is quite natural. If we do it mathematically, then this will go down numerator and this will come in the denominator, and it will be 1 by gamma, and so this will make the same conclusions. Another say question. If we do this, here P, here V, reversible adiabatic expansions for the two gases, one for a nitrogen and other for neon. What will be the nature of these curves starting from this same initial state? Suppose this is the initial state. So this will be the curve. Suppose here P1 and V1, and it is the adiabatic process for say nitrogen. This is final P2 and V2, and this is V2, and this one is V1. If we do this curve, for neon, in this case neon is greater. For this neon, gamma value 1.66. For nitrogen, this gamma is equal to 1.40. So this curve for this neon, it will be steeper, then it will be like this. And this is for neon. Both are adiabatic, both are reversible. Both volume change will be the same, but here it will be P2 dash and V2. So for this neon, P2 dash will be less than this P2. P2 dash will be less than P2. So this is another type of questions generally asked in this interview. Next. Now let me describe the Joule's expansion. It is also called the free expansion. The gas is expanded against a vacuum, means a zero pressure. Here it is one bulb which contains this gas at pressure P, and here the vacuum. This there is no pressure in this bulb, and here it is the stopcock, and whenever the stopcock will be open, this gas will move from this side to this side. And here also one thermometer is placed to see whether any temperature change occurs for this free expansion of this gas. This is the very simplest, most experiment, and these walls of these two bulbs are wrapped with insulator so that no heat can enter into this system between the two. And this is very popularly known as a Joule's expansion. So if we consider the first law of thermodynamics, first law of thermodynamics, then it is Q plus W equal to du. Or we can write also this Q is 0. Q is 0 as it is adiabatic walls. No heat can enter into this system or this bulb. And this W equal to, if W is the work done by the surroundings, then it will be minus PdV. Minus PdV. This P is the external pressure into PdV. But here the external pressure against which this gas expands, if we open this stopcock, then this gas expands, and this is, if this is V1 and this is V2, then final volume becomes V1 plus V2, and this external pressure in this case equal to 0. So 0 into volume change, this is also equal to 0. Work done by the gas or work done on this gas, both will be equal to 0. Or if we state this one, then it is work done by the gas, and in that case P externally 0 means W equal to 0. It is very surprising that whenever the gas expands against this vacuum, against 0 pressure, the gas cannot do any sort of work. Why it becomes? I can explain here. In the case of adiabatic system, in the case of reversible process, this is P external, and this P external, and it is P internal. And suppose P internal is greater than P external, and this is decreased slightly, and piston moves to some extent, and there is a small volume change. Again, this external pressure is decreased, and the piston moves. And if it is V1, then ultimately in a multiple steps or infinitesimal small steps, it will go to this V2. Whenever this external pressure is changed infinitesimally small amount, in that case the gas molecules, in this gas molecules, put this brake thrust of this piston in a streamline flow or the laminar flow. All the molecules will move in a laminar flow, means all the molecules will run in a parallel fashion, like the parade in police line or this military camp. So whenever there occurs a streamline flow of this gas molecules to thrust this piston, it does some mechanical work. But whenever this P external equal to 0, so these gas molecules will move in a random fashion. In that case, this molecule will move in a random fashion. V1 to V2, and P external equal to 0. In this case, molecules move in a turbulent flow, and no thrust to be given on the piston to raise this piston, and there will be no work. This is our explanations why the external pressure, when it becomes equal to 0, the work done is also equal to 0, as P external equal to 0. So you can see this one 0, this one 0, so du, this is work done by the gas. So du also equal to 0. This one 0, this one 0, du equal to 0. So u is constant. So this sort of expansion, either Joule's expansion or free expansion, this is also the expansion in which the internal energy of this gas remains constant. So it is called the constant internal energy expansion of this gas. So this U is constant. We like to determine. We like to find an expression of this mu j. Mu j means Joule's coefficient. It is called Joule's coefficient. Joule's coefficient of this gas, and this is defined as del T by del V at constant U. Whenever U remains constant, then it will be the change of this gas for this expansion of this volume dV amount. So we like to find out an expressions of this mu j. We know this U is a function of temperature and volume. So du equal to del U by del T at constant volume into dt plus del U by del V at constant temperature into dt. By partial differentiation we are getting this one. So for this process, for this expansion, for this free expansion, du equal to 0. So 0 equal to, and this one is the Cv or one mole gas, Cv and dt, and plus del U by del V at constant temperature into dt. So dV, this is dV and this is dV. So dt by dV, so del T by del V at constant U, here internal energy remains fixed, it will be equal to minus how much? Del T here 1 by Cv and del U by del V at a constant temperature. At constant temperature. So del U by del V, this is the isothermal expansion, and here T equal to, and this is equal to this mu j. So minus mu j into Cv. It is very interesting to see here this process. This Q equal to 0 means this expansion is adiabatic process, and also du equal to 0. And if we consider this ideal gas, then du equal to Cv dt means the temperature is also fixed. du equal to 0, so dt equal to 0 means T is fixed. So this process is very unique in the sense that this process is isothermal as well as adiabatic. No such process occurs which are simultaneously adiabatic and isothermal, but it is a special case you can consider. So actually Joule himself determines the value of this mu j, and his experiments are having the poor setup. Experimental setup is very poor, was very poor, and so he was unable to determine this small change of this gas. So he found that mu j equal to 0. So when as Joule's findings mu j equal to 0, then del U by del V at constant temperature equal to also 0. But later on, the Case and Shears in 1940, they repeated this experiment by the greater setup, by this more improved setup, and they found that there is a slight change in temperature as found by this not thermometer. They have used the very precision temperature recording instrument, and they found that there is a slight change in temperature. Whenever there is slight change in temperature, then mu j are not equal to 0. Whenever expands a constant internal energy, the temperature slightly changes, dt delta is not equal to 0. So mu j not equal to 0. So actually del u divided by del v at constant temperature is also not equal to 0. This is non-zero. Cv is fixed value, so this one is non-zero, as according to the case Sears experimental findings. Now it is taken granted that this relation is valid for this ideal gas, and this relation is valid for the real gas. This relation is valid for the ideal gas, isothermal expansion of this gas, there will be no change in internal energy, and for this real gas, isothermal expansion of this isothermal expansion, in case of this real gases, there will be change in internal energy. And if we consider the van der Waals equation, then it will be A by V square for van der Waals equation. Van der Waals equation means this is positive. What does it mean? In this expansion, isothermal expansion of this gas, van der Waals gas, there will be increase in internal of the system. This is all about the discussions, relations between temperature, pressure, volume for this ideal gas and reversible process, and also the Joule expansion. And also I have explained the Joule's free expansion. Joule's free expansion. In my next lecture, I shall discuss the one very important thermodynamical property, and this is the enthalpy. So thanks to you all who are watching this video.